Have you ever wondered why a skyscraper can sway in the wind without collapsing, or how a stadium roof can span hundreds of feet without intermediate columns? Or maybe you've been in a meeting with a structural engineer and heard terms like live load and seismic load and nodded along, but didn't fully grasp the implications for your design. Understanding structural loads isn't just an engineering exercise, it's the fundamental language of safety, efficiency, and innovation in architecture and construction. If you don't speak this language, you're designing in the dark. Today, we're pulling back the curtain on the 5 primary types of structural loads that shape every building you've ever set foot in. By the end of this video, you'll not only know what dead, live, wind, seismic, and snow loads are, but you'll understand how they directly influence the form, material, and details of your architectural projects. This knowledge is what separates great designers from mere drafters. Let's start with the most permanent and predictable of all, the dead load. In simple terms, the dead load is the weight of the building itself. This includes every permanent, static element, the weight of the structural steel or concrete, the floors, the walls, the roof, the mechanical equipment permanently bolted down, and even the permanent finishes like tile and brick cladding. It's called dead because it doesn't move. You can calculate it with a high degree of accuracy during the design phase by knowing the material densities and volumes. For example, a reinforced concrete slab might weigh 150 pounds per square foot, PSF. A steel beam might be so many pounds per linear foot, and a brick veneer wall adds a specific weight. A pro tip from seasoned structural engineers: always do a realistic dead load estimate early in your design. A common and costly mistake is for architects to assume lightweight construction and then later specify heavy granite floors and massive green roof systems without communicating this to the structural engineer. This can lead to under-designed foundations and beams, requiring expensive redesigns. The dead load is the constant baseline upon which all other loads are added, so getting it right is non-negotiable. Now, let's talk about the variable, moving weight. The live load. Unlike the dead load, the live load is not permanent and can change in magnitude and location. This is the weight of all the people, furniture, equipment, and movable partitions within a building. Think of the occupants in an office, the books in a library, the cars in a parking garage, or the goods in a warehouse. Because we can't predict exactly where and when these loads will be, we use conservative values prescribed by the building code, specifically the International Building Code, or IBC. For instance, a typical office floor might be designed for a live load of 50 PSF, while a library reading room might be 60 PSF, and a heavy warehouse could be 250 PSF or more. It's crucial to understand that live loads are not just about the floor. They also account for impact loads, like the force from a jumping crowd in a gymnasium. The architectural implication here is massive. The required live load directly influences the depth of your floor beams and the size of your columns. If you're designing a flexible space that could one day change from offices to a filing archive, you need to communicate that to the engineer so they can use the appropriate live load from the start, avoiding costly structural reinforcements later. Next, we move from the loads inside the building to the powerful forces of nature acting upon it, beginning with wind load. Wind load is a dynamic lateral pressure that pushes against the exterior surfaces of a structure. It's not a constant force. It suctions, it pressures, and it creates complex vortices around buildings. The design wind pressure is calculated based on several factors outlined in the code: the building's geographic location and basic wind speed, its height and exposure category, is it in an open field or a dense city, and its importance factor. A critical architectural concept here is the lateral load resisting system. While dead and live loads are primarily gravity loads carried vertically down to the foundation, wind load is lateral. It wants to push the building over. To resist this, we need elements like shear walls, braced frames, or moment frames that act as the building's backbone, transferring these lateral forces down to the foundation. The shape of your building has a profound impact on wind loads. A tall, slender box will experience significant sway and wind pressure, potentially requiring a tuned mass damper, while a curved or tapered form can significantly reduce wind forces. This is where architecture and engineering meet. Your aesthetic choices have direct structural consequences. In many parts of the world, the most critical lateral load isn't wind, but seismic load. Seismic load, or earthquake load, is fundamentally different from wind load. While wind pushes against the outside of the building, an earthquake's ground shaking forces the entire structure to move at its base. The inertia of the building mass, remember our dead load, resists this movement, generating massive internal forces. The key principle here is ductility. A seismic force wants to twist, shake, and rack the building. Brittle materials like unreinforced masonry will simply crack and collapse. Therefore, seismic design focuses on creating a ductile, flexible structural system that can absorb and dissipate this energy through yielding in specially designed elements, like the beam-column connections in a moment frame or the links in a braced frame. The architectural implications are enormous. The structural system requires a regular, symmetrical configuration and continuous load paths. Large, irregular openings in shear walls, soft stories where one level is much weaker than others, and heavy overhangs can be catastrophic in an earthquake. Your job as a designer is to understand these principles and work with the engineer to create a configuration that is both architecturally compelling and seismically resilient. Finally, for projects in colder climates, we have snow load. At first glance, snow load seems simple. It's the weight of accumulated snow on the roof. But it's more complex than that. Snow load is influenced by the ground snow load for the region, the roof's shape and slope, its thermal properties, is it a warm roof that melts snow? And its exposure to wind. A flat roof will accumulate more snow than a steeply sloped one. But interestingly, a complex roof with valleys, parapets, and changes in height can lead to drifting snow, where wind piles snow into specific areas, creating localized loads several times higher than the average. This is why you often see collapsed canopies or awnings after a heavy snowstorm. They were designed for a uniform load, but not the extreme drift loads. From an architectural standpoint, your roof design is directly dictated by snow load. The need for a steeper pitch, the placement of drains to prevent ponding, which adds even more load, and the design of roof structures to prevent these dangerous drifts are all critical considerations. It's a perfect example of how climate and site-specific conditions must directly inform your architectural vocabulary. So, how do we make sense of all these different loads acting simultaneously? We don't just add up the maximum of each one. That would be overly conservative and inefficient. Instead, we use load combinations as specified in the building code. These are probability-based equations that consider the likelihood of different loads occurring at their maximum values at the same time. A common combination might be 1.2 times the dead load plus 1.6 times the live load plus 0.5 times the snow load. For lateral loads, we might combine dead load plus live load plus either the full wind load or the full seismic load, but not both, as a major earthquake and a hurricane don't typically happen at the same time. Understanding these combinations is the key to efficient design. It allows structural engineers to right-size members without over-designing, saving material and cost while maintaining safety. As an architect, grasping this concept helps you understand why your engineer might be more concerned about a certain load in a specific design scenario. It's the synthesis of all these forces that leads to a safe, efficient, and buildable structure. Now I want to hear from you. Which of these loads has most surprised you in how it influences design? Was it the complexity of seismic loads or the hidden dangers of snowdrifts? Let me know in the comments below. If this deep dive into structural loads was helpful, please give this video a like and subscribe to the channel for more content that builds your professional knowledge. Thanks for watching.